Welcome back, Algebra 3. We are in Lesson 7. We're going to talk about inductive and deductive reasoning today, focusing mainly on logic. So inductive reasoning, actually let me type it, probably better on your eye sockets and your eyeballs and all that eyesight thing. If I type it for you, you'll be able to at least read it. So inductive reasoning is when Miss Tracy cannot really spell. All right. Inductive reasoning is the process of finding a rule. And by that I mean, the experimentation and the data collection that is used to find the rule. Like, for instance, if you were to take a coin and you were to flip it 100 times, and then you were to discover that half the time it's heads, half the time it's tails, because you did it enough times that you got a good sample set, and you kept getting the same the same ratio. That's when you have good sample set, is when the ratio remains static. Right? If you do 10 and you get 6 out of 4 as heads, you do 20 or 10 more, and then the next 4 out of 10 are heads. The one that you got 10 out of 10 is heads, and 10 out of 10 is tails. And you do another 10 and you get another 10, and you keep coming back to 1 out of 2 is going to be one or the other. Then you have found a good rule, right? And that's the typical. You've proven the numbers and the physicality of the coin, that you have two sides, and when it lands you're getting it one of the two sides. That's your probability rule there. Now, deductive reasoning is different. It is using a rule that already exists, using an existing rule to prove something else. That's deductive reasoning, and that's what we use when we do logic. We're not collecting data, we're not making experiments. We're using deductive reasoning by using an existing rule. We are given an existing rule of some kind and another statement to compare it to find or draw a conclusion. So, for instance, let's do this one. All frogs are green. Now, I never said the rule had to be true in logic. This is obviously not a true statement. And all frogs are green is what we call the major premise. And the major premise is going to be your rule, right? This is the rule that you're using. And our minor premise is the specifics, the member of the rule, member of the set the rule applies to. So let's talk about Henry. Henry is a frog. So this is going to be your minor premise, and your minor premise is your member. That is the member of the set as specified by the major premise. And your conclusion is going to be Henry is green. And typically we say, therefore, Henry is green, but I'm, typing in me. That's your conclusion. And your conclusion is going to be, how shall I say this? Contain the predicate of the major premise and the subject of the minor premise. So it's going to be P is S for the second. So let me illustrate what that means when I say P is S. So we have here a subject, all frogs. That is our set. So our subject is something. This is a predicate nominative. The predicate tells us what the subject is. So the S is P, right? Take that out. So S and P. S is P. Henry is a member of the subject. He's a member of S. And then, so we would repeat S here. We have to say that the subject here is a member of the subject here. So the member is the subject. All right, see the pattern? You have to tie the major and the minor premise together by having the subject of the major premise as the predicate of the minor premise. If you don't have that, then you're not following a logical set of steps. You're not tying these two together. They have no relationship between the two to link them. They have to have that relationship. So your conclusion is when you are able to tie the member of the set to the predicate condition by having these two linked. So I am able to say, if all frogs are green and Henry is a frog, then Henry, which is the member of the frog family, is green. That's my MP. So if you can follow, so I typed this wrong. It should be M is P right here, not P is S. Sometimes I do that. M is P. So that's what you're wanting to be able to do, is tie these two characteristics together by having them within the same set. They need to be a part of the same family or group in order to have this specificity about Henry and draw this conclusion about Henry. If you didn't have that all frogs are green and all you had was Henry is a frog, well, we can't draw the conclusion that he's green because we don't know anything about frogs, right? This is what it's telling us. It's telling us about frogs. Henry's a frog. Therefore, what is true about frogs is true about Henry. All right, so let's do a couple more. Let's look at one that maybe doesn't work. Okay, so here's one that doesn't work. If it rains, I will go to town. It did not rain. I did not go to town. And you might be thinking to yourself, okay, so that makes sense, right? That makes sense. Does it really though? Let's look at it. If it rains, so the condition of it raining is our subject and going to town is our predicate. It did not rain. It didn't rain. This does not say anything about it not raining. It only talks about if it does rain. So therefore, this has absolutely nothing to do with the major premise. The minor premise has no link to the major premise at all. So now you might say to yourself, but it's just the opposite. But that doesn't matter. It does not matter. Opposites, they have to have a relationship. And opposites, if it is not something, right, just because it rains or not doesn't rain, those two conditions are different conditions. And so they have to have the exact same condition in order to be linked together. So going to town, yeah, that's the other predicate, but we still cannot draw a link to these because it not raining is not a member of the set of it raining. Now we could adjust that. Let's see how we could fix that. If I said, let's see, let me delete this and I'm going to delete all of this. If we rewrote this and we said it rained on Monday, right? Then I could say on Monday, actually, I would have to rewrite that. I would have to say Monday it rained. So Monday I went to town. Now if you look at it, it follows the pattern. I have a major premise that says, if it rains, I'll go to town. Now we have a minor premise that matches the condition of it raining, right? So they're linked. It rained, right? So this Monday is when it rained. So Monday, I went to town. That is how you have to look at it like that. You have to be very specific and know that whether or not the condition matches exactly when you have these if-then statements. And we'll talk some more about the if-then statements, but they're very particular and they're very picky. And there's a workaround on how you can figure out if the conclusion is valid or not. And that's what we're looking for. This is what we call a valid conclusion or a valid argument. And the argument itself, the entire thing, is called a syllogism. And let me spell that out for you. Syllogism. And a syllogism is where you have a major premise, a minor premise, and the conclusion. So this whole thing is a syllogism. That's not a very good rectangle. This is your example. This is the pattern that you need in order to have a valid conclusion. Now, a valid conclusion isn't necessarily a true conclusion, right? Because we know that all frogs are not green. There are red frogs, there are blue frogs, there are white frogs, there are green and orange frogs. There's all types of different colored frogs in this world. So it's not necessarily truthful. We're not looking for truthfulness. We're looking for valid logic. Does this follow the pattern? Does it make sense? And if it does, it's valid, whether or not it's 100% accurate in the real world. What we have to look at is this is a world unto itself, and we are following the rules set forth in this little world, the world of this syllogism. Okay, and this is a G. That's a Y, so if you can see that a little bit better. All right, so let's look at a couple more examples. And I'm going to type because I know how bad my handwriting is and I hate to hurt y'all's eyes. All right, so here we go. Here's the first one. Let me scooch down and give you another one here. We'll do all of them at once. Go ahead and write them as I'm writing them so that we can be on the same page. I'm not necessarily going to have the best grammar and punctuation. I'll do the last one here. All right, so these are all the examples that I have for right now. So let's look at these. All normal dogs have, it should be an S there, all normal dogs have 4 legs. That dog has 4 legs. That dog is a normal dog. All right, so I'm going to use my highlighter and find the subject. So all normal dogs is our subject, all normal dogs. It's not here. It's not here. This is our P is here and here. So we cannot, this is invalid. It doesn't follow the right pattern. And the right pattern is P to S, or actually, I'm sorry, S to P, and then M to S, and then the conclusion has to be M to P. That is what we have to have in order for the syllogism to be valid. And right now we have S to P. This is our rule. This is our member. So that dog is the member. 4 legs is the predicate. It is not the set. So we cannot, it doesn't work. It's invalid. All right, so let's look at this one. We have all boys. That's our set. And the predicate descriptive is good, or predicate nominative. That child, that's the member, is a good child. Again, that's a predicate. It doesn't match. It doesn't line up. So this is an invalid statement as well. It doesn't work. Because what if that child is a girl? Just because that child is a good child, that could be a girl. There's not that relationship. But if you had said that child is a boy, then you could say that child is good. You cannot reverse the conclusion and the minor premise. It just does not work. It is not sound logic. And don't stress too much about all of this. It's more about kind of prepping your head, getting you ready for proofs, more than having to memorize a bunch of terminology. So don't focus too much on the terminology, but do know, kind of what it is when you see it again. Okay. Let's look at the last one. All chickens have 3 legs. Here's our set, all chickens, and 3 legs is our predicate nominative, or our condition, or our predicate descriptor, however you want to refer to that P. Henny Penny is the member we're talking about of the set of chickens. So S and S. Henny Penny is the M, and 3 legs is the P. So this is a valid statement. Now again, valid doesn't have to be true in our world. It just has to be true based on what rule we're given in our major premise. So this is a valid. This is the only valid one we have in this list. So let's look at another one. And this one is going to be a little bit difficult, and we're going to have to use some techniques to figure it out. So here is the argument. All right. So let's look and see what we have here. All non-athletes are vegetarians. All right, I typed that wrong, and that's going to make a difference, so I need to fix it. Jim is a non-vegetarian. Therefore, Jim is an athlete. That's really confusing. So what we have to do is we have to use something here. When we have negatives, when we don't have a statement of this is this, right? We have a negated subject set here. When we have a negated subject set or a negated predicate, we have got to do some analysis. And the analysis is going to be the use of a contrapositive. And a contrapositive comes from turning this into a double negative, basically. We're going to negate both sides and switch them. So we would take our subject and our predicate here, and we would turn it into an if-then statement. So if they are a non-athlete, then they are vegetarians. So we're going to use a contrapositive. If this is S, right, this is our S, and this is our P, then what we're going to do is we are going to use the negative and swap them. So now we want to have a negative S, or actually, that would become S to P would become negative P to negative S. That is a contrapositive. That's when you take the S and negate it, and the P and negate it, and then change places. Let me make this look more like an arrow so it's not confusing. It doesn't look like a negative inequality. So the contrapositive for this would be if non-vegetarian then the opposite of this would be athlete. Or the negated form. When you negate something, you're not a non-athlete, then you are an athlete, because double negatives make a positive. We know that from mathematics. A negative times negative is positive. The same is true in language. A double negative makes a positive. So we just took the opposite of each one of these and flipped it. If it helps you to remember, contrapositive is like when you multiply an inequality by -1, you change the sign and you flip it. You flip the sign. So effectively you flip places, right? You swap them out because the arrow remains pointing in the same direction, right? But if you flip location, it's like you flip the sign. So now we can take this contrapositive and put it in for our major premise so that we can see if this makes sense. So now we can just reword it. I think I'm going to type it so that it is readable. So let's look at this. So I'm going to reword this as a major premise. All, if I can get this to type, there we go. All non-vegetarians are athletes. Jim is a non-vegetarian. Jim is an athlete. Okay, so now when we look at that, because we had this negated part here, we were able to flip it. We have non-vegetarians is our S, and athletes is our P. Jim is our member, and non-vegetarian is our S. Therefore, M is P. Therefore, this is a valid argument. And something about contrapositives, if the contrapositive is always true. It's always true. Think about when we say, when we treat an equation, if we do it to one side, we do it to the other side, that keeps its value. It makes it remain equal. The same is true for the contrapositive. If we do the same thing to both sides, right, then it remains true. It remains equal. So that's what we're doing here. Right? We're doing the same thing. We're negating both sides. Because it was an inequality, we flipped it. But then that still made it remain true. So we're not doing really any new concepts. We're just applying them to language and to logic so we can see the patterns here. And you're going to want to use this a little bit whenever we start working on proofs. It's going to come in handy for the way that you think about those proofs and how you're able to go from one step to the next step, which is one of the reasons why I really couldn't get deep into proofs last year in Algebra 2, because it is a whole other concept. It is all about the logic. But if you follow this pattern and you're able to create a contrapositive that follows, if all you change is the contrapositive is always true. And true, we mean that it says the same thing as the original major premise. If all non-athletes are vegetarians, then all non-vegetarians are athletes. It says the same thing. It is a true statement, right? So let's look at some new terms I want you to think about and use. And this is why we would use a contrapositive. I'm not going to clear the page. I'm just going to come down here. There are two other things. So if we have S is equal to P, right? S leads to P. If this, then this. And a contrapositive is where we negate them and flip them. and we know that it is true, right? This is your major premise. This is your contrapositive. The inverse of the major premise is going to be P. If P, then S. This is the inverse. And if you think about what that means, we just inverted the major premise. We just flipped it. That's what the inverse statement is. Now the converse statement, think about how we got the contrapositive. And I'm starting to write contrapositive instead of converse. And not the shoes. I think that's right. Let me look at this. I'm sorry, I got it backwards. The converse is the opposite here. The converse is where you flip it. It's the opposite. P is equal to S. The inverse is where you now apply the negative to that. So the inverse would be the inverted contrapositive. So that would be negative S is negative P, or the opposite of P. So the major premise is S is P. The contrapositive is the opposite of P is the opposite of S. And this is always true. All right. These two are always, or I should say, valid. All right, the converse and the inverse are not always true. They're not. So let's try that and see. Let's see if we can prove that. So let me get a little bit of room here. So let's pull something that we know from geometry. Let's say, all squares probably need to type that too because, you know. All right, we'll do it like this. So the major premise, all squares have 4 equal sides. Okay. The contrapositive is where we would flip that and say, if 4 equal sides let me take that back because we have to negate it. So if not 4 equal sides, not a square. So you see how that works. All squares have 4 equal sides. If it's a square, it has 4 equal sides. The contrapositive would say, if it does not have 4 equal sides, then it is not a square. It is the complete opposite of the major premise. However, it is true. It is true. The converse to that would be if it has 4 equal sides, if 4 equal sides, then it's a square. That's not always true. A rhombus has 4 equal sides, but it is not a square because it does not have 90-degree angles. So therefore, the converse here is not true. The inverse here is also not true because the inverse would be the negative S, which is if it's not a square, if it's not a square, then it doesn't, then four sides not equal. That would be the best way to write that. So if it's not a square, then the four sides are not equal. Well, that's not true either. Because if you have a rhombus, again, then you could have four equal sides, but it's not a square. So that's not true either, because a rhombus disproves the converse and the inverse statement, which is why we use the contrapositive instead of a converse or an inverse to help us prove the negated major premises. Excuse me. All right, so there's only one other thing I wanted to tell you guys about, and that is when we have what's called the if, two F's statement. And the if stands for if and only if. That is what that is short for. And the if and only if just means that they're equal. That would be the equal symbol, right? And an example of that would be all right angles are 90 degrees. Okay. The converse of that would be not 90 degrees, not a right angle. That's true. That is true. If it's not 90 degrees, it's not a right angle. That is the contrapositive. What about the converse? The converse would be that 90 degrees is a right angle. That is true. So the converse is true. What about the inverse? Not a right angle. Not 90 degrees. That is also true. So when you have an IFF, which is an if and only if, or an equal statement like this, then it is called an if and only if because the major premise, the contrapositive, the converse, and the inverse are all true. And it's because it is an equal statement, right? It is an equal statement, and it is what we would be like an A equals B situation. And the way that we would write that, an if and only if symbol or illustration would be P if and only if. Sorry, I got that backwards. S if and only if P. That's how we would write that and say that. All right angles are 90 degrees. That is an if and only if statement because the S is equal to the P and the P is equal to the S. All right, and that is all we have for lesson 7, and I will see you in lesson 8.